Okay, so in this lecture, again, we're going to continue with the problem that we were doing in the previous lecture. In the previous lecture, we were discussing a problem where we were discussing that if a surface charge density is glued on the surface of the sphere, and that particular surface charge density is given by sigma naught sine 2 theta sine phi, then how would we be able to find V inside as well as V outside? Okay, and I told you on the previous day that in order to find this V in and as V outside, we must first be able to we must be in a position to find ALMs and BLMs. Okay, and what are these ALMs and BLMs? This is what it is. So ALM and BLM one must be able to understand. So ALM R raised to power L YLM theta comma phi, and V outside would be BLM divided by R ki power L plus 1 by LM theta comma phi. So these are V inside and V outside. Uh, First, we have to find this ALM and BLM. If we are not able to find this ALM and BLM, then we will not be able to find this V inside and V outside. This is one thing. What I did was I tried to write this surface charge density in terms of spherical harmonics. So what was my plan? My plan was that somehow I'll be able somehow if I'm able to write these charge density in terms of spherical harmonics, and sigma naught sine to theta sine phi, I wrote it as sigma like iota sigma naught root over 8 pi upon 15 y21 plus y2 minus 1. One of the conditions on the potential is that your potential is continuous on the boundary. So this is what I've done. BLM is equals to ALM R ki power 2L plus 1. So this is one thing that I already know. And another condition is that my perpendicular electric field, that is a normal component of electric field, is discontinuous at R. So what does it mean? It means that potential minus del V upon del R outside, is outside the surface, minus again this will be plus del V upon del R at R equals to R minus should be equals to sigma upon epsilon. If this is the case, and sigma you already know, this is iota, I'll write it here, iota sigma naught, and then there is some root over 8 of pi upon 15, and then there would be some y 2 1. Okay, sorry. Okay, so this is y2 1, and then this is y2 minus. I hope it is clear. Okay, so what I will do, I know that potential outside is given by uh, potential outside is given by BL. So potential outside is given by BL upon R raised to power L plus 1. This is M if I write M. So the YLM theta comma phi, and there is a summation going all over on L and M. So what I'll do, I'll take a derivative of it. So derivative would be equals to what? This will be minus L plus 1 BLM divided by R ki power L plus 2, and then this is YLM theta comma phi, and this I have to evaluate at R equals to R. Okay, so this will be like L plus 1. Here you will have BLM, and then you have the spherical harmonic YLM theta comma phi, and divided by R ki power L plus 2. And then you have this plus, you will have L, and again you will have this, I think, AL, and then M, again you will have R raised to power L minus 1. Okay, and then we'll have y lm theta comma phi, because the derivative of R ki power L will be L R ki power L minus 1, and R equals to what we placed. And I think this will be equals to what? This will be equals to sigma. This is like sigma on epsilon root over 8 pi upon 15, and then this is y21 plus y2 minus 1. Okay. Now, if I sum it all over, from the expression itself, I'm able to understand that only y21 and y2 minus 1 terms can be expanded on the right hand side, and no other terms, because no other terms are there on the on the left hand side. I can only expand this expression for L equals to 1 and M equals to plus minus 1, and for all other terms, there are no such terms on the right hand side. So all other ALMs and BLMs will be 0. So only I would write only terms corresponding to I should write only terms corresponding to L equals to 1 and L equals to 2 and M equals to plus minus 1 would survive. All the other terms of ALMs and BLMs are 0. Is that clear? So what I will do, so first thing that I have to do is, so if I just write L equals to, let's say, if I write L equals to, L equals to 2 and M equals to plus minus 1. So L equals to 2. So if I write L equals to 2, M equals to 1, and if I divide it by L equals to 2, this will be like 4 here, and this will be like 3 here, and this will be like Y 2 1, and then again 3 B 2 minus 1 divided by R raised to power 4, and again you will have this Y2 minus 1. Again, if I see L equals to 2, if I write it here, it will be A 2 1 R raised to power, this will be 1, and this will be Y 2 1, and then 2 A, like this is minus 1, and again this will be like R raised to power 1, and then you have this Y2 minus 1. I hope it is clear. And this is all I legated to iota sigma naught epsilon naught root over 8 pi upon 15, and then you have this Y2 1, and then this you have Y2 minus 1. So if you equate these two terms, and you can clearly see that Y2 1, here you have Y2 1, and here you have Y2 1. Okay, and here you have Y2 minus 1, and here you have Y2 minus 1. Okay, is that clear? So what I can write, if I want to write, like if I want to add these three, like add these terms up, what I will find. What I can do instead, I can use another boundary condition. So another boundary condition dictated, okay, sorry, there was another boundary condition. So what does another boundary condition state? That ALM is equals to R, sorry, BLM is equal to ALM R ki power 2L plus 1. So I'll use that boundary condition so that things become a little bit easy for us. So I'll write it here. So BLM is equals to ALM R ki power 2L plus 1. So I think that is it. 2L plus 1. So I think it is, I'll write 2L plus 1. Okay, and only L equals to 2 term is there. So L equals to 2 term is there. So what I'll write 3 times B2, I will write A 2 1, and there would be R ki power 5 here. So I will simply write R, and then you have this 3. Again, I will write A2 minus 1, and again you will have R ki power 4 written here, R ki power 5 written. So R, see, understand my point. What I want to say that B21 will be like A21, and this will be R ki power 5. And again, if we write B2 minus 1, this will be like A2 minus 1 R ki power 5. Okay, so this term will remain, and then you have this, I think, some term 2, 8 to 1, and then you have this R. Sorry, again you have this term also written here. I'm forgetting all these things. Okay, A to 1, R ki power 1, Y to 1, and then you have this plus 2, A2 minus 1, R ki power 1, Y2 minus 1. Now I think you are in a position to compare both of the sides. So what will be it? I think if I want to write, what will be my A2? If you simply compare, this will be like 3 here and 2 here. So this is like 5, A, 2, 1, R, Y, 2, 1. Again, this is 5, A, 2, minus 1, R, Y, 2, minus 1. And this is, I think, equal to iota sigma naught upon epsilon naught root over 8 pi upon 15. You have this Y2, 1 plus Y2 minus 1. I hope it is clear. And if you compare these two terms like Y2 1 and y2 minus 1, you can see that whether I write like these two terms are almost like they're similar. So I'll write a2 plus minus 1 is nothing but it is equals to iota sigma naught upon 5 epsilon naught root over 8 pi upon 15. I think there would be some r as well here, and there would be like this is how it is. Okay. And what would be my b uh, 2 uh, plus minus 1? It will be equals to what? It is like a2 plus minus 1 r की power 5 here. So this will be like iota sigma naught r की power 4, because r की power 5 होगा. Here it will be like r की power 5 into a2 plus minus 1. So this will be like 5 epsilon naught. R की power 5 is here, divided by r. So I have written r की power 4. 8 pi upon 15. I hope it is clear. So you know now b2 plus minus 1 and a2 plus minus 1. These two are the terms. Okay. Now, if I want to write, potential inside, if I want to write potential anywhere inside, what will be it? What will be it? So if I want to write my potential inside, I know my potential inside is given by summation ALM, and then this is I think uh, ALM, I think R raised to power L, and then this is YLM theta comma phi. So I know that only my L equals to 2 and M equals to plus minus 1 terms are surviving. So I'll replace it all over here. So what it will come out as? It will come out as uh, because a2 plus minus 1 are similar, so I'm not going to bother much. R equals to L is only like L is 2 only, so I will write R square here. I don't have any other option. Okay, so it will be like iota sigma naught upon 5 epsilon naught R, and then there should be R square. Okay, and 8 2 plus minus 1, this is what, acha, there will be some root over 8 pi upon 5 as well. I think this is 5 or 15. I think this is, is there a mistake that I've done somewhere? I don't know. Just give me a minute so that I am in a position to get back to some mistake if there's some mistake. I don't think there is a mistake somewhere. I think this is 8 pi upon 15 only, no? Right? So I think this is 8 pi upon 15 only. Okay, 8 pi upon 15. And then there is some, there will be two terms like y2 1 plus y2 minus 1. Okay, y2 1 plus y2 minus 1. And you know that y2 1 and y2 minus 1, what are those terms? Those are like 15 upon 8 pi, and this was minus, this was sine theta, cos theta, and you had, I think, if I correctly remember, it was iota e की power iota 5. This was y2 1, and if I correctly remember, y2 minus 1 is root over 15 upon 8 pi, and then I can simply write it as, why should I not write it as sine 2 theta divided by 2 e की power minus iota 5. Is that clear? So at least I should write it here also. Like I will do that. So what I will do, and this will be like iota sigma naught upon 5 epsilon naught r, and then there is r square, and then this is root over 8 pi upon 15. And again, if you write it as root over 15 upon 8 pi sine 2 theta upon 2, this is something very common I've written. What I can do, I can write it as minus e की power iota phi plus power minus iota. No, sorry. Is that so? Okay, okay, that is fine. Okay, so now if you just try to replace this entire thing by minus 2 iota sine phi, so this minus gets dissolved. Iota square is minus 1 and minus minus plus 2 gets cancelled. This gets cancelled. So forget about it. Forget about it. Forget this negative sign. Forget this iota. So overall, what you'll get, I think you'll get sigma naught upon, this is r square, this is 5 epsilon naught r, and then you will have some sine 2 theta written, and then you have this sine phi. Okay. And once you know this potential inside, you can find potential outside as well. So in order to find potential outside, one needs to use this condition summation BLM upon r raised to power L plus 1 YLM theta comma phi. And also I know that here also only terms corresponding to L equals to 2 and M equals to plus minus 1 would survive. So if I use those terms, I'm leaving it to you as a homework. The solution would be like V outside would be equals to what? Sigma naught. The same way I've done, you have to do it same way. Sigma naught r ki power 4 upon 5 epsilon naught r cube. And then there should be sine 2 theta. And then there would be some sine phi. So overall, this is how you're going to do the questions in if you want me to do right now, I'll do it. Okay, that would be good thing for you. So what I'll do, I'll expand this term. So I'll get b to 1 divided by r cube, and this will be like uh, y to 1. And then again b to minus 1. This will be again divided by r cube, and this will be like y to minus 1. And let us first write this term. So this is like b to 1 and b to minus 1, they were both same. So I'll write it in this fashion only, r cube. Yeah, if you remember, I had done this thing that b21 and b2 minus 1 are similar. So I've written this in compact form in this way. And what would be it? So if I just like use this particular expression, I'll use it all again so that you don't get confused. So this will be like root over minus root over, I think it is 8 pi upon 15. If I'm not wrong, let me just check it again, because once we have 15 upon it, this is what is the problem. Because if I do it wrong, then things will become wrong. So like this is 15 upon 8 pi, and then this is sine 2 theta divided by 2, and then you have this e ki power iota phi, and then this is plus root over 15 upon 8 pi, and then you have sine 2 theta divided by 2 e ki power minus iota phi. Okay, so this is how it is. b2 plus minus 1 divided by r cube, and this is like if you just take root over 15 upon 8 pi common out, and sine 2 theta also common out, what you will get? I think we'll get minus uh, iota sine phi, because you see there is a 2 here. So e ki power minus iota phi minus e ki power iota phi. So this will be like minus 2 iota sine phi, and this 2 gets cancelled, so minus iota sine phi. Okay, and now what is b2 plus minus 1? Replace that thing. So b2 plus minus 1, if I correctly remember, this is, if I can copy it, let me see if I can copy it. Okay. 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 So this. Okay, just give me a minute. I thought it would be easy for me to copy. However, it is getting slightly difficult. Just give me a minute. But चलो कोई बात नहीं. I think this is it. So instead of copying, I should have written it. That was way too easy. Just give me a minute. Okay, so let me do. Just let me do. So what is b2 plus minus 1? b2 plus minus 1 was, I think, if I b2 plus minus 1 was equals to okay. So this is, there is some problem. Okay, so this is like b2 plus minus 1 is iota sigma naught r raised to power 4 upon, this will be like 5 epsilon naught root over 8 pi upon 15. Okay, so if you use this term here, so what I'll get, I will simply get iota. Iota is iota square. This will be minus minus plus. This sine 2 theta and sine phi would survive anywhere. So I'm writing potential outside anywhere would be sine theta, sine phi is fine. And then you have this 5 epsilon naught written. 8 pi upon 15 would get cancelled. Forget about it. R cube power 4 would anyway remain. Sigma naught would anyway would remain. This 5 epsilon naught will anyway remain, and R cube will remain. So this will be sigma naught R cube power 4 5 epsilon naught upon R cube sine to theta sine phi. This is what I have written right here. Okay. So I hope everybody has got this particular way of dealing with such problems. But I will I want to tell you that these problems are not going to be asked that much in examination, because these are very difficult things to do in examination. Now let us try to do one more problem. And I think that would serve as a final thing to this particular topic. So case of, I'll write, if you remember that we did a case for conducting a sphere placed in a uniform electric field. Now we are doing a case of a conducting sphere. We are doing a case of conducting sphere of radius capital R placed in an external electrostatic field, given by E vector is equals to E vector is equal to minus x, sorry, this is plus x j cap and then y I cap. Okay, and we want to find what are the what we want to find. We want to find potential inside as well as outside. And also, I told you that because of the influence of the external electric field, there would be some induced distribution of charges. There would be some induced charges. So we want to find what would be the induced charge density due to the external electric field. Okay, so this is what we are going to find. So if my electric field is given by E vector is equal to x j cap plus y I cap, the uh, first thing is that we must be in a position to find what is the potential corresponding to it. See, because we are doing a problem in Laplacian equation. So what is the first thing that arises is, what is the potential that gives rise to what is the potential uh, what is the potential, what should I write? So what is happening is that now this electric field is kept in the electrostatic field given by x j cap plus y I cap plus x j cap, and we want to find what is the potential inside as well as outside. And the second thing is that what is the induced charge density due to this external electric field given up. Okay, so what will first we have to find what is that potential corresponding to this particular field. So if you remember that your potential, if I write minus xy, so I can write that minus grad V is equal to electric field, isn't it? Or I can simply take minus del V upon del X as the component of electric field along x-axis, and minus del V upon del Y as the component of electric field in the y direction. So that is another way. So if you do this also, you'll get to this. Okay. So in general, what is the potential all around? A potential all around is equals to minus xy, x in spherical polar coordinate is r square, and this is sine theta, sorry, this is r sine theta sine phi. And what is this? So this is r sine theta cos phi. So in general, the potential as a function of r theta and phi, you are getting minus r square sine square theta sine phi. So you can see that this is a problem where you do not have some azimuthal symmetry. Your potential is dependent upon phi. So all around in the space, there would be this potential. And you know that there are as such no charges present. There are as such no charges present. So if I want to solve a Laplacian equation in spherical polar coordinates, it uh, it will give you an idea. So all around in the space, the potential is given by this expression, that is minus r squared sine squared theta sine phi. I want to find what is, like, in general, this is the potential which is this particular sphere is subjected to, and this particular potential you can clearly see that contains this phi term. So I have to solve a Laplacian equation. I have to solve a Laplacian equation. I have to solve this Laplacian equation in general. I have to solve this Laplacian equation in general, and I know that the general solution to this is given by summation ALM r raised to power L plus BLM upon r raised to power L plus 1, and then you should have PLM, sorry, YLM theta comma phi. In general, this is the field. Okay, and now even as r tends to infinity, your potential is not becoming like it is not becoming, it is not becoming uh, 0. See, r tends to infinity, your potential is still infinity. Okay, so what I will do, uh, what I will do, the first condition is that whatever potential is there on the surface, this must be continuous. So potential on the surface must be continuous. The first thing is potential. I don't know what is. I know that in general, this uh, conducting sphere is subjected to an electric field, and that electric field is somehow a non-uniform thing now, and it is like like this is x j cap plus y I cap, or I can say that this particular conducting sphere is now surrounded by a potential, because of which there would be some potential inside as well outside. Because see, if this sphere was not there, then the potential would be this. But now, because of the presence of the sphere, this potential anyway inside and outside would change. So this is what we have to see. So first thing is that whatever be the potential must be continuous inside as well as potential must be continuous on the boundary. That implies if I want to write V inside and V outside are R equal to R, they must be equal. That is first thing. And this will give you, I think, ALM r की power L is equals to BLM r की power L plus 1. So in general, I will write that my BLM okay, again, sorry, this is mistake. Uh, sorry, just give me a minute. Okay, no, sorry. Okay. My mistake. Just give me a minute. Just give me a minute. Sorry. So I actually got carried away. Uh, got carried away. Sorry. So now understand, this is not the case of general. So now I cannot write inside is this potential, outside is this potential, because see, even as r tends to infinity, your v is not tending to 0. So no longer can you write that this is uh, like this is my outside potential and this is my inside potential. So what I have to do, first thing, I know that my conducting sphere, the surface would be at equipotential. The surface would be an equipotential surface. Surface would be equipotential because this is a conducting surface. So surface would be equipotential, no doubt, because of the presence of the charges. There would be some induced distribution of charges inside. Like inside, there would be some what I can say. Inside there would be some induced distribution. But overall, understand that the surface would be in equipotential, and let us do the way Griffith does. He says that take that equipotential to be 0. So you just take that potential on the surface should be 0, so that it simplifies our thing. If you remember in like whenever we discuss this azimuthal symmetry, I took phi equal to potential equals to phi naught on the surface. So instead, if I want to say that if my surface is equipotential, I can simply say that let the potential be equal to 0. After all, it is some constant. So why not take 0 to make our things easy? And in general, now potential, I cannot write inside as well outside in this fashion, that inside is this and outside is this. Why? Because in general, we have to write my potential to be in this form. Because see, now no longer my potential is tending to infinity as r tends to infinity. So this is one thing that one must remember. So in general, your potential at r equals to r must be equal to what? 0, because it is an equipotential surface. Overall, understand the point that this will be like ALM. I think r की power L would be equals to minus BLM upon r की power l plus 1, or in general I can write BLM is equals to minus ALM, and this is r की power 2l plus 1. I think it is clear. Understand again the point that since it is a conducting sphere, so the surface would be an equipotential surface. Also understand that there would be some induced distribution inside because of the presence of an external electric field. But overall, this particular surface would be an equipotential surface because this is a metallic sphere. And let us take that potential to be constant and that constant be zero, so that things become easy. Otherwise, I will have to write some phi naught, and then there would be some phi naught term here. And then there, like, things can be solved easily that way. Things can be solved that way also. But overall, understand that this phi naught would be an additive term only. So why not take it zero? So if I've taken it zero, so BLM would be minus ALM r की power 2l plus 1. R की power 2l plus 1. Okay. So overall, my potential term will now become, overall, the potential term will now become, I think it will be like summation L comma M ALM r raised to power L minus r raised to power 2l plus 1 divided by r की power L plus 1. And then you have this Y LM theta comma phi. Okay, so this is how it is. So potential will now become this way. Okay, this is one thing. Also understand that as r tends to infinite, my potential would be like, it is given that this particular conducting sphere is surrounded by potential given by minus r square sine theta minus r square sine theta. I think it was sine square theta. And just let me check. Okay, sine square theta sine phi. So this is so all over. This is minus r square sine theta sine phi, and you can see that even as r tends to infinity, this is not tending to zero. Rather, it is tending towards infinity only. So what will happen now? No longer I can write that this is my infinite. Like, this is my term outside. Now this term certainly has some infinitely large contributions. So my potential outside will now also contains ALMs. So this is what I made a mistake. I was in hurry also. I made that mistake. So excuse me for that. But overall, understand what I'll do. As r tends to infinite, this term would go to zero. Only this term would remain. And I will have to write this term in terms of some spherical harmonic so that things become easy. So what I'll do, I will write my potential in terms of spherical harmonics. Had I written this particular thing? No, I have not written it. So I will write my this term. So understand where sine square theta was coming. If you remember, sine square theta was coming in y22. So y22 was equals to what? Y22 was equals to, I have the list along with me. So y22 is, I'm writing it as 1 by 4 root over 15 upon 2 pi, root over 15 upon 2 pi. And then you have the sine square theta, and then we have e की power iota 2 phi. This is how it is. And if I write y2, I think minus 2 also. Now this is minus 1 की power 2. So this will remain the same. This will remain same. This will remain same. Sine square theta would remain same. Here I will have e की power minus iota. Minus 2 iota. Okay, so this is how it is. So if I want to write this sine phi, I will have to, I think there is some mistake somewhere. I don't know what is that mistake. Let me check it. So potential was, okay, this is not only sine phi, this is cos phi as well. Okay, because this is this cos phi, sine phi is here, sine square theta is here. Okay, so cos phi would also remain here. So now at least things are coming the way we want. Okay, sorry. So here it will have some, we'll have some cos phi as well. So what I'll do, I will first write my potential V as minus r square sine square theta sine 2 phi divided by 2. At least now things are easy. And also understand, again I'm saying, now no longer as r tends to infinite, your ALM would be 0. So initially what we used to do, we used to say that our potential is 0 at infinity. So what we do, we take ALM as 0, And we see that potential outside is just given by BLM upon r की power L plus 1 by LM theta comma phi. But now, since at infinity also your potential is infinitely large, so your ALM term would survive. Okay, so this is something that one needs to remember. So now, in this case, your ALM terms would survive, and uh, terms would survive as r tends to infinity. So we have to find that as r tends to infinity, what these ALM's term would be. So both of side, you know that you can clearly see that L equal to 2 term would survive. L equal to 2 term would survive if you compare these two terms, but that is what I'm trying to do also. So what I'll do, I will write this potential as a function of, as a linear combination of y22 and y2 minus 2. So this potential, I can write it as, I think if you just summarize it, I think it would be, okay, so this is minus r square upon 2. Okay, this is fine. I have written in this fashion. Okay. And what will be it? Like if I write y2 2 minus y2 minus 2, so it will be like 1 upon 4 root over 15 upon 2 pi. This is fine. Now we'll have sine square theta. This is absolutely fine. And this e की power iota 2 phi minus e की power minus iota 2 phi. This will be like 2 iota. And this will be like the sine 2 phi. Okay. So if I want to write like sine square theta and sine 2 phi, so I will have to divide it by 1 upon 2 iota. I will have to multiply it by 4. I have to divide it, multiply it by 2 pi upon 15. And then I can write it as y22 plus y2 minus 2. This is how I'm going to write it. Is that clear? I think it is clear. So overall, this 4 would get cancelled. Forget about it. This iota, if you multiply both. So my potential anywhere, I can write in terms of iota r square root over 2 pi upon 15. This will be y22 plus y2 minus 2. So this is my potential. This is my potential, which is equals to iota r square root over 2 pi upon 15 by 2 and by 2 minus 2. Okay, sorry, this is minus now. And subtract. Sorry, minus. Sorry. Okay, so this is how it is. This is fine. So this is potential anywhere in the space. Now, as r tends to infinite, you know that my potential in general for the sphere, conducting sphere, is given by ALM r raised to power L, I think minus L plus 2L plus 1 divided by r की power L plus 1, and I had this YLM theta comma phi. So this is this is the potential of a sphere which is kept in a potential which lacks the azimuthal symmetry. So this is the potential of the sphere. And if I take r tends to infinite, this term would go to 0. Forget about this term. And only term that survives is this. So if I compare both sides, so iota r square root over 2 pi upon 15, and this is y22 minus y2 minus 2. And if I compare both of these terms, like both on both of the sides, if I try to compare, on both of the sides, if I try to compare, I can find my A21 and A22 and A2 minus 2. This is what I can get from both of the sides. Is that clear? I mean, is that clear? On both of the sides, we can find that. So I can write only term corresponding to L equals to 2 and M equals to plus minus 2 would survive. Would survive. And I will write that my A21, A22, sorry, so this is A22 R square Y22 would be equals to what? So it will be equals to iota root over 2 pi upon 15. This is fine. I think this is clear. If you compare on the both sides, A22, this will be like r की power 2, r square is here, and this is y22. So compare both of the sides, you'll get iota root over 2 pi upon 15. And if you write A2 minus 2, what it will be? It will be equals to, I think, it will be equals to iota, and then there will be root over 2 pi upon 15, and then there will be a negative sign. I hope it is clear. So these two terms one has to remember. Okay, these two terms we have found. Okay, now this is something that we have done as r tends to infinity. Okay, so in general we are only left with the terms a22 and a2 minus 2. So I can have in terms of I can only have terms b22 and I can only have terms b2 minus 2. So what was b22? B22, if I remember, it was minus of a22 r ki power 2l plus 1. So instead of 2l plus 1, I'll write 5 here. And similarly, I'll write here minus of a2 minus 2, and you will have r ki power 5. This particular thing I've got by assuming that the potential on the sphere, uh, potential on the sphere, because since it is a metallic sphere, so it is an equipotential surface, why not take it 0? So BLM was related to ALM in this way. So I'll write A22. If A22 was there and only A2 minus 2 was there, so only B22 and B2 minus 2 term would survive, and they are equals to A22 into r ki power 5. B22 will be equals to what? A22 r ki power 5, and B2 minus 2 would be minus A2 minus 2 r ki power 5. In any case, this is it. So overall, I know these terms, and now potential anywhere can be written. I've written already that, like potential any. So this is like, even this was not required, because potential in general. In general is given by. So like, instead of writing that we are finding potential inside as well as outside, because that in this particular thing I can not write inside and outside. I will have to write general potential only. Okay, so I wrote the problem as be inside and outside. Here this particular problem does not make sense. So because see, we want to just find what will be potential in general. So I'm just writing potential in general, because you see, uh, we do not have like we do not have those things here. In the initial cases when we were discussing, we were writing that inside potential would be equals to ALM r ki power L by L theta comma phi, and outside my potential would be BLM upon r ki power L plus 1 by LM theta comma phi. So this is what we were writing initially. Okay, but now since my conducting sphere is subjected to some external potential which is not uniform, so now I would not write inside and outside here, because even outside would contain some terms of ALM. So that is a problem. So what I'll do, I'll write potential in general. So potential in general uh, can be written as summation. This is what I wrote, ALM, and I think if I'm not wrong, I wrote it r ki power L here, and here we had r ki power of minus r ki power of 2L plus 1 divided by r ki power n. So instead of even writing this b22 b2 minus 2, I will use this expression, because like r ki power 5 will anyway, because see, this is nothing but b lm upon r ki power L plus 1 term hi to hai. This is, so I have replaced this already, so why not use this by lm theta comma phi. So now understand the point that potential in general would be given by this expression, that is ALM r ki power L minus r ki power 2L plus 1 upon r ki power L plus 1 by LM theta comma phi. And now we will only have terms corresponding to L equals to 2 and M equals to plus minus 2. So you will only have these two terms. Other terms would get nullified. So if you use these two terms, I think if you use these two terms, you will get A2 2, and this is r square minus r ki power 5 upon r cube, and then again this will be like y22. I mean, these all questions are usually not asked in the examination, so don't worry about it. Minus r square r ki power 5 upon r cube, and then you will have another term y2 minus 2. Okay, so this is it. Now what needs to be done, this is you can take this common out, and you know that there is a negative here, otherwise the term is same. So I'll use iota root over 2 pi upon 15. Okay, and then this is r square up minus r की power 5 upon r cube is here, and you have y2 2 minus y2 minus 2 here. Okay, and this y22 minus y2 minus 2, if you remember, we've done it here. y22 minus y2 minus 2, this was 1 upon 4. I'll write it somewhere so that I don't have to speak. 1 upon 4 root over 15 upon 2 pi, and then you have this sine square theta 2 iota was again there, and sine 2 pi was there. So overall, this is the term that I'm going to copy it somewhere down. Let me use it here. Okay, so this will be like iota is there, root over 2 pi upon 15 is here, and then this is r square minus r की power 5 upon r cube is here. And then instead of all this thing, I'm going to write 1 over 4. I'm going to write 1 over 4 root over 15 upon 2 pi. And then I'm going to write sine square theta. Then I'm going to write 2 iota. And then I'm going to write sine 2 phi. Okay. So overall, this will get cancelled. I'm not worried about it. Iota will become, this will be like minus. So there will be minus here. This 2 will get dissolved by 2 here. So this 2 will be right here too. So this will be like minus r square minus r की power 5 upon r cube. This entire thing in commonality. 2 will be here. Sine 2 phi divided by 2 will be sine phi cos phi. So this is minus minus r square minus r की power 5 upon r cube sine square theta. And then I can simply write sine phi cos phi, because sine 2 phi is 2 sine phi cos phi divided by 2. So overall, this will be my potential in general, because of the presence of a conducting sphere uh, in the potential given by minus xy. So like this is a very difficult problem. So this is potential in general. Potential in general. I hope it is clear. So this is the form of the potential, and it was expected that we would also find the induced distribution. So induced charge distribution, if a conducting sphere is placed in a potential minus xy, you can say, or you can say your electric field is, it was given by, I think, x j cap plus y I cap. This was your electric field which was given to you. If this is the electric field in which your conducting sphere is subjected, there would be some induced distribution. I don't know what would be the pattern of that distribution, because it's not uniform. So overall, there would be some induced distribution, and we want to find this induced distribution. So we know that this is a conductor. Anywhere near the conductor, we know that electric field normal component is given by sigma upon epsilon naught. And from here, I can find what will be the induced distribution would be epsilon naught, I think, minus del V upon del R at R equals to R. So this is what I have to do. So it will be like minus epsilon naught. Del V upon del R would be minus. Again, minus will become plus. Like, so let me write plus here. Del V upon del R would be 2R minus R की power 5. This will be, I think, plus 3 upon R की power 4. And then there would be sine square theta. There would be sine phi, and then there would be cos phi. So I hope this will be like induced distribution of charge. This will be, I think, 5 epsilon naught R sine square theta sine phi cos phi. So in now your induced distribution will depend upon theta and phi as well. So I hope this is clear to you. I hope this is clear to you. If you find certain difficulty, kindly let me know, and we'll see all those difficulties in next session. I would like to tell you that these questions are usually not asked in the examination because of the certain sense of complication. You can see the amount of time it requires to be done in the examination. So you can be like, you can keep these things only for possibly interviews. You can prepare them for interviews. Otherwise, overall, the first question that I did today, like in the previous session that I did, was a potential one, and the other question that I did was like if the surface charge density is glued, that can be asked, but such questions are not asked. Also understand that in this question, like previously we had the question for a uniform electric field. So we had this like a conducting sphere placed in a electric field E naught k cap. So there we did minus del V upon del Z E naught. So I wrote that my potential in general is given by E naught Z, or Z I wrote in R cos theta. Similarly, here we have to find the potential in general. So we have to find potential in general. And what I was doing wrong was in between, I lost my mind somewhere and I was doing something wrong. So again, I'm telling you, this is a potential which you can see that as R tends to infinity, this is not tending to infinity. So now no longer you can say that this is inside and this is outside. So now we have to find uh, two conditions. The first condition, that being this conducting sphere, uh, this particular surface would be equipotential. And second thing, even as R tends to infinity, your ALM terms now you cannot reject them overall. So there would be some contribution from ALM terms. So this is a slightly difficult problem for you, but overall I hope I'm able to explain the idea. I hope to meet you in the next lecture. Till then, take care.